Hey everyone! In this video, we're going to be taking a look at special parallelograms in the coordinate plane. More specifically, what I want to take a look at is how do we justify, how do we prove that a quadrilateral is a rhombus, a rectangle, or a square when we're working in the coordinate plane. Now remember, we've done this with parallelograms already, where if we graph a quadrilateral in the coordinate plane, and if we want to justify that it is a parallelogram, we have a couple of theorems or definitions to help us out. For example, the definition of a parallelogram is two pairs of opposite sides that are parallel. So I could use the slope formula to find the slopes of the opposite sides, and as long as we have those two pairs that match up, we knew that it was a parallelogram. Well, for rectangles, rhombuses, and squares, we have theorems that will help us justify as well. So let's begin just by taking a look at those. So for all of these, the first thing we do need to know is that we do have a parallelogram. Once we know it's a parallelogram, we can use one of the following theorems or corollaries to justify that it is a rhombus, a rectangle, or a square. So let's just go through these and I'll explain quickly how we can use this. So the first one, a rhombus corollary. This says that all four sides of a rhombus are congruent. So in the coordinate plane, I can use the distance formula to find the lengths of all four sides of my quadrilateral, and if they're all the same, I know I have a rhombus. The second one, the rhombus diagonals theorem. This theorem says that the diagonals of a rhombus are perpendicular to each other. In the coordinate plane, I can find the slopes of the two diagonals, and if those slopes are opposite reciprocals, that means that they're perpendicular. And if they're perpendicular, we have a rhombus. For a rectangle, we can use the rectangle corollary, which says that a rectangle has four right angles. In this case, I could do this with the slope as well. I could find the slope of all four sides of my quadrilateral, and if we have those two pairs of opposite reciprocals, that's going to give us four right angles, which is going to give us a rectangle. The second one here, the rectangle diagonals theorem. This theorem says that the diagonals of a rectangle are congruent to each other, or they have the same length. So in the coordinate plane, I can use the distance formula to find the lengths of the diagonals, and if they match up, I know that I have a rectangle. And lastly, for a square, if I want to justify that something is a square, I just need to show that it is a rhombus and a rectangle. So those are the theorems and corollaries that we can use to justify. Now let's take a look at an example. So I have a parallelogram ABCD. They're already telling me that it is a parallelogram. And I have the vertices -2, 6, 6, 8, 4, 0, and -4, 2. And I want to determine if this is a rectangle, a rhombus, or a square. So let me start by graphing this parallelogram. So we have A is at -2, 6. So -2, 2, 4, and 6. So here's point A. Point B is at 6, 8. 1, 2, 3, 4, 5, 6. And then up at 8. Point C is at 4, 0. 1, 2, 3, 4. And then our last one, D, is at -4, -2. So 1, 2, 3, 4, and then down 2. There's point D. And now I'll just connect these points together to form our parallelogram. All right, so here's our parallelogram ABCD. Right away, just by taking a look at it, it looks like we don't have a rectangle. I'm saying that because it doesn't look like we have right angles. But we may have a rhombus, and I do need to justify that. I also am going to need to justify that it's not a rectangle. So the way that I like to do this is I actually like to use the diagonals in both cases. So working with the diagonals, we can show that this is or is not a rhombus, and we can also show if it is or is not a rectangle. If the diagonals are perpendicular, it's going to be a rhombus. If the diagonals have the same length, it's going to be a rectangle. So let's start by finding the slopes of the two diagonals. So let's take a look at diagonal AC. So the slope here, I can use my slope formula, subtract the y values in the numerator, subtract the x values in the denominator. I also have a graph, so I could just count the slope. Taking a look at rise over run, looks like we have a slope of -1. Let's just verify that by using our slope formula. So subtracting the y values, we have 0 minus 6. Subtract the x values, we have 4 minus a -2. So we end up with 6 over 6, which does simplify to 1. So we end up with -6 over 6, which does simplify to -1. And now for the other diagonal, BD, again, we could just take a look at the graph and we could count it out. It looks like it has a slope of +1, judging by the graph. But let's verify by using our formula. So subtracting the y values, -2 minus 8, and subtracting the x values, -4 minus 6. Here we get -10 over -10, which does simplify to +1. -1 and +1, those are opposite reciprocal slopes. So yes, these are perpendicular, and we have the right angles at the intersection of the diagonals. Now, just to verify whether or not this is a rectangle, let's take a look at the length of each of these diagonals as well. So for this, we can use the distance formula. So the distance formula, we subtract the x values. So we have 4 minus -2, so 4 plus 2 squared. Subtract the y values. It's going to be 0 minus 6 squared, and the square root of all of that. So this is going to be 6 squared plus 6 squared, so 36 plus 36, so we end up with the square root of 72. And I'm actually just going to leave that like that, because I'm going to just compare it to what I end up with for BD, so I don't need to get a decimal approximation for that at all. So let's just do the same thing for BD. Subtract the x values, so -4 minus 6 squared. Subtract the y values, -2 minus 8 squared. And the square root of all of that. This is going to be -10 squared plus -10 squared, so that's 100 plus 100. So we end up with the square root of 200. So the diagonals, they don't have the same length. They are not equal to each other. But the slopes are opposite reciprocals. So with all of that said, ABCD is a rhombus. So ABCD is a rhombus. And then let's just summarize what we found. So this is a rhombus because we ended up with the diagonal AC is perpendicular to the diagonal BD, but they do not have the same length. So AC is not congruent to BD. So because the diagonals are perpendicular, that gave us a rhombus. Because the diagonals did not have the same length, we know it's not a rectangle, which also means that it can't be a square. So our parallelogram is a rhombus, and that's how we can use these different theorems or corollaries to justify a special parallelogram in the coordinate plane.